A buffer solution is a solution which resists large changes in pH when either acids or bases are added to it. Notice that the definition says resists large changes in pH. That means that when I add an acid or a base to my buffer solution, there will be a change in pH, but it will be a small change in pH or a slight change in pH. And what we will see is that a buffer solution is a solution that contains appreciable amounts of a weak conjugate acid-base pair. Buffer solutions are frequently prepared in labs to maintain optimum conditions for chemical reactions. So let's say you are doing a chemical reaction, and in order to maximize the amount of product or to maximize the percent yield of the reaction, it had to be run at a very specific pH. Let's say it had to be run at a pH of, let's say, 6. So you would run the reaction in a buffer solution that would maintain that pH near 6. Again, you might get a slight change in pH that deviates from a pH of 6, but the buffer solution would resist large deviations from that pH. Buffer solutions also occur naturally. Blood, for example, is a complex natural buffer solution maintaining a pH of approximately 7.4, optimum for oxygen transport. The major buffering agent in blood is a mixture of carbonic acid, H2CO3, and bicarbonate ions. The basis of buffer action is the establishment of an equilibrium between either a weak acid and its conjugate base or a weak base and its conjugate acid. Let's take a look at a weak acid and its conjugate base. The weak acid being acetic acid, shown here, and the weak base or the conjugate base of acetic acid is acetate. So I'll write that in here. This is acetate, or the acetate of polyatomic anion. Since acetic acid is a weak acid, it's only going to partially dissociate. So I'm going to use my reversible reaction arrows like this. So acetic acid will partially dissociate in water to produce hydronium ions and my acetate ion. The way that the buffer functions is in accordance with Le Chatelier's principle, which states that an equilibrium system, when stressed, will shift its equilibrium position to relieve that stress. Now, what would happen if I added a base, hydroxide, to a buffer solution? Adding a basic substance to a buffer is going to cause a change. What's going to happen is that the strong base, hydroxide, is going to react with the strong acid, hydronium. And if it reacts with the strong acid shown here, my hydronium, if it consumes that hydronium, the amount of hydronium is going to drop. And what that's going to do is it's going to cause the equilibrium to resist that stress. Therefore, my equilibrium is going to shift to the right. What does that mean? It means that my weak acid, acetic acid, is going to dissociate to form more hydronium ions. So the loss of hydronium, the stress, is compensated by the dissociation of the acid, meaning acetic acid, to produce more hydronium. What's the net result of this? The pH will not remain unchanged, but the net result is to maintain the pH close to the initial level. Now, what would happen if I was to add a strong acid or hydronium to my buffer solution? Well, adding an acidic substance to a buffer is going to cause the following changes. The hydronium from the acid that I'm adding will increase the overall concentration of the hydronium, right? I'm just increasing the number of hydronium ions. So that's more hydronium ions per volume of my buffer. Therefore, the concentration of hydronium is going to increase. The conjugate base in the buffer is then going to react with that hydronium in order to form more of my weak acid. So what it's saying is if I increase the amount of my hydronium, well, I have a weak base right here, and that base is going to react with that hydronium and push the equilibrium to the left to produce more of my weak acid, my acetic acid in this case. The net result is to maintain the hydronium ion concentration and the pH close to the initial level. Again, it's not going to be identical to the initial level, but it will be close. Now in this case, since we're adding an acid, we would see a slight decrease in the pH. To summarize, the gain of hydronium, or the stress, is compensated by the reaction of the conjugate base to produce more of the weak acid, acetic acid in this case. The effects of the addition of a strong acid or a strong base can be summarized as shown here. If I were to add strong base to my buffer system, what am I doing? I would be consuming hydronium, or it would be reacting with hydronium. The net result is that my acetic acid is going to have to dissociate and push the equilibrium to the right to try to reestablish my hydronium ion concentration. If I add a strong acid to my buffer system, what's going to happen is I'm going to increase the amount of hydronium, which will in turn react with my conjugate base and drive the equilibrium to the left in order to produce more of my weak acid. Again, in both of these cases, in terms of pH, if I'm adding my strong, in terms of pH, when I add that strong base to my buffer system, the pH is going to increase, but only slightly. And if I add a strong acid to my pH, and if I were to add a strong acid to my buffer system, the pH will drop, but again, only slightly. Buffer capacity is a measure of the ability of a solution to resist large changes in pH when a strong acid or a strong base is added. More specifically, buffer capacity is described as the amount of strong acid or strong base that can be added to a buffer solution without significantly changing the pH. If we look at this concept from the viewpoint of our acetic acid acetate buffer, the buffering capacity against base would be a function of the concentration of the weak acid, acetic acid in this case. Buffering capacity against acid would be dependent on the concentration of the anion or the acetate ion. Buffer solutions are often designed to have an identical buffer capacity for both acids and bases. In the example here, this would be achieved when the concentration of the acetate and the concentration of the acetic acid would be equal to each other. As an added bonus, making the concentration of acetate and acetic acid as large as practical ensures a high buffer capacity for both added acid and added base. The buffering process is an equilibrium reaction described by an equilibrium constant expression that's shown here. So I have my weak acid, acetic acid plus water, dissociates or partially dissociates because it's a weak acid to give me the acetate, anion, and hydronium. And in Chapter 7, we looked at how to solve an equilibrium expression for an equilibrium constant. Now, because we're talking about an acid here, instead of using K equilibrium, we say that our constant, our big K, we call it Ka. So this is the equilibrium constant for the dissociation of my weak acid. If I solve for my Ka, I see that Ka is going to be equal to the product of the concentration of my products divided by the concentration of my acetic acid. Of course, I leave water out because it's a pure substance. And now that I've got this expression, if I want to know the pH of a buffer, all I'm going to have to do is solve this for the concentration of hydronium and then plug that concentration of hydronium into the formula pH is equal to minus log times the concentration of hydronium, and then I'd have my pH of my buffer. Well, with that in mind, let's take a look at a specific example. It says, calculate the pH of a buffer solution in which both the acetic acid and the sodium acetate concentrations are 2.0 times 10 to the negative 2 molar, and they've also provided us with the Ka for acetic acid, which is 1.75 times 10 to the minus 5. Well, we wrote down the expression for Ka on the previous slide, so all we have to do is solve this expression for the concentration of hydronium. So the first thing I would do is I would multiply both sides by the concentration of acetic acid, which would get me to this expression here. And then I would divide both sides by the concentration of my conjugate base. Anyhow, in the end, I end up with the concentration of my hydronium is going to equal to the Ka multiplied by the concentration of acetic acid divided by the concentration of my conjugate base. And so when I use this formula that the concentration of hydronium is equal to the Ka multiplied by the concentration of my weak acid, in this case acetic acid, divided by the concentration of my conjugate base, in this case the acetate ion, when I plug the numbers in, so here's my Ka, 1.75 times 10 to the minus 5, I see that when the concentration of my acid and my conjugate base are equal, they're going to cancel out, and I get that the concentration of my hydronium is equal to my Ka. I plug that into my expression, pH is equal to the minus log of the concentration of the hydronium. And since there are 3 sig figs in my concentration, I will report my pH with 3 numbers past the decimal place. So I get a pH of 4.757. The solution of the equilibrium constant expression and the pH are sometimes combined into one operation. The combined expression is called the Henderson-Hasselbalch equation. For the acetic acid sodium acetate buffer system, I have my Ka, which we already established. If I take the minus log of both sides, I get this expression here. Now you might recognize this term right here, minus log of the concentration of hydronium, that's equal to pH. And we're going to look at how we define minus log of Ka. And the minus log, Ka, is actually the pKa, just like the minus log of the concentration of hydronium is the pH. Now we can rewrite our expression. pKa is equal to pH minus the log of the concentration of our conjugate base divided by our acid. And if we solve that expression for pH, we get that the pH is equal to the pKa plus the log of the concentration of the conjugate base divided by the conjugate acid. And from that, we can make a generalized expression for any weak acid conjugate base buffer, which is this, the Henderson-Hasselbalch equation, that pH will equal pKa plus the log of a conjugate base divided by the concentration of the weak acid. Let's take a look at a couple of questions that come from our textbook. Question 8.99, which of the following are capable of forming a buffer solution? If we take a look at A, we have ammonia and ammonium chloride. And I know that ammonia is a weak base. And a buffer solution has to be the combination of a weak base and its conjugate acid, or a weak acid and its conjugate base. And it just so happens that when ammonia, NH3, takes on a proton, I produce its conjugate acid, which happens to be ammonium. So this is my conjugate acid, and the conjugate acid will come in the form of a salt. And so ammonia and ammonium chloride will form a buffer solution. In B, it asks HNO3 and KNO3. So this is nitric acid and potassium nitrate. Now you'll remember that a buffer solution has to be either a weak base in its conjugate acid, like an A, or a weak acid in its conjugate base. But nitric acid is a strong acid. Nitrate is the conjugate base of nitric acid, but since nitric acid is a strong acid, this will not function as a buffer solution. The next question asks us the same thing. In A, we have HBr and magnesium chloride. First of all, hydrobromic acid is a strong acid, so this is not going to be a buffer solution. Also, chloride is not the conjugate base of HBr, and thus A will obviously not form a buffer solution. In B, I have carbonic acid and sodium bicarbonate. Well, carbonic acid is a weak acid, and bicarbonate is its conjugate base in the form of a salt in sodium bicarbonate. So carbonic acid and sodium bicarbonate will form a buffer solution. Question 8.107, what is the concentration of hydronium for a buffer solution that is 0.200 molar in acid and 0.500 molar in the corresponding salt if the weak acid Ka is 5.80 times 10 to the minus 7. So we have our buffer solution, which is made from a weak acid and its corresponding salt. So let's write down a generic equation. If I have a weak acid and I put that in water, it's going to partially dissociate to give me the conjugate base of the acid plus hydronium ions. Now we're given the Ka, so let us write down an expression for the Ka. And the Ka is going to be equal to the concentration of the conjugate base multiplied by the concentration of hydronium divided by the concentration of the weak acid. Of course, we're going to leave water out because it's a pure liquid. Now, what is the question asking us to do? It's asking us to solve for the concentration of hydronium, this right here. So all I need to do is rearrange my formula to get the concentration of hydronium. I've gone ahead and done the algebra already. So the concentration of hydronium is pretty easy to solve. It's going to be equal to the Ka multiplied by the concentration of the weak acid divided by the concentration of my conjugate base. Now I've got my formula. I can plug in my numbers. So I'll just start down here. The concentration of hydronium is going to be equal to my Ka, which is given to me here, 5.80 times 10 to the minus 7, multiplied by my concentration of acid, which is 0.200, and divide by the concentration of my corresponding salt, which is my conjugate base, so 0.500. I've gone ahead and done the math already, and the concentration of my hydronium ions will be 2.32 times 10 to the minus 7 molar. Now that's all the question is asking us for, but of course we could go ahead and calculate the pH if we wanted to. And to do that, we would use the formula that pH is equal to the minus the logarithm of the concentration of hydronium. We could do it just for fun. So we would take the minus log of 2.32 times 10 to the negative 7. And we would end up with a pH equal to 6.635. Again, there are 3 sig figs in my concentration. So I write down my pH with 3 numbers past the decimal place. Now again, it's not asking us to solve that, but it's always fun.